Bueno, buenos días a todos. Bienvenidos a este segundo día del curso de SILICONOMY. Permitirme esta primera presentación, será en inglés. Tenemos a Axel Harman. Axel completed his studies in electrical engineering at the University of Stuttgart in 1996. In his 28 years career at Siemens, Infineon Technologies and Intel, he held numerous technology and manufacturing-related positions in the semiconductor industry. During 2006-2010, he was delegated to Singapore to lead some foundry supplier management activities on Infineon, gaining diverse international experience on technology operation and commercial aspects. In 2011, he moved with the acquisition on Infineon mobile business to Intel. Welcome to Intel. From 2011 and 2021, he was heading the foundry supplier management at Intel. In his leadership position, he managed Intel's business in Silicon Foundry manufacturing partners. In 2021, finally, you joined Intel Foundry Services Group to lead its business development in Europe. Then thank you. The stage is yours.
Thank you for the introduction. So I'm happy to be here. Happy to have the first presentation, not before lunch where everybody is tired. So let me give you a kind of introduction from the SILICONOMY to the Silicon Foundry business. So I prepared quite some slides. I hope you are fresh and can get everything quickly. Okay, so I will talk you through the SILICONOMY, getting a starting point. I'm aware you had this topic already yesterday, so I will keep it short. Then talking about leading technologies, because for Europe, this is really very important that we get a step into the leading technology topics here. We are very strong in kind of the mature specialty technologies in analog, RF, in sensors, in microcontrollers, but on the leading technologies, that is where we need to close some gaps. Then I will talk about silicon foundries in general, and then going into the Intel's open system foundry. And at last topic here, also talking about the attractiveness of semiconductors for the young talents to go into the segment and to make a big change here in Europe to close our gaps. So let me start off with SILICONOMY. So this is about the magic in the silicon. So what we have seen over the last decades is really a big change in our world, in our society, with computers, with smartphones, with a lot of other things. So this is what we call SILICONOMY, the impact of the silicon products to our economies. Very transparent, few examples in the 60 years ago, transportation, how it looked like, how it looks today or tomorrow. Robotaxis are coming up. Entertainment, now we are streaming music, we are streaming videos, so a lot of different applications coming up. So the world is really changing quickly. Communications, everybody is super aware, is not comparable with previous days. So what we have seen is over the last 5 years, there have been 4 times the number of connected devices coming in. So this was already a change where a lot of us have experienced, wow, the world is changing a lot. Imagine, over the next 10 years, 15 times more connected devices will come. So our world will change even much more. So this is a great opportunity, and being part of that, that is where we need to be here. So all this is mainly driven by some of the technology superpowers. So talking here about the compute, the connectivity, the cloud-to-edge infrastructure, artificial intelligence as a very great hype over the last year now. So a lot of demand coming in from artificial intelligence now. And not to forget sensing, super important to really kind of translate the analog to the digital world. So if you look into what is happening over time, we come from the mainframe to the client server, so some connectivity is starting. The cloud mobile time where we are living today mainly, or at the end of that here in the graph, that already made us working with the internet and all these new technologies, 5G. But what is really coming up now is an orchestrated compute. So a lot of devices talking to each other, if it's smartphone, smart home, automotive, industrial applications. So a lot of devices will get connected and will get smarter, will create value out of the data processing and the interpretation and the decision which may be taken by those systems to help the human beings. So what we see is that in 2030 we will have a semiconductor market size of $1 trillion. So this is a tremendous number. And what is really important to understand is that 30–50% of that will be connected with AI machine learning aspects. So this will go through all the different application segments. If it's data center, mobile compute, automotive, networking, IoT, kind of everything will get into that, and artificial intelligence will need a lot of compute power. Therefore, it's important to also address those advanced and leading technology node businesses here in Europe. So I think this is quite obvious here. The semiconductors are critical to the global economy. In the US, they have done some market assessment. So 39% of the GDP output is generated with a semiconductor product as a major primary input factor. So a lot of the kind of GDP is linked into semiconductor. And in the left lower chart, you see the numbers of the 2021 semiconductor market in the each segments. So you see the compute and the smartphone businesses with $170 billion market size are the two bigger ones, and currently we see that the HPC, so the compute segment, even takes off further. So this will be even outgrowing the smartphone market, which was dominant over the last decade. And then we have the automotive, the consumer, the industry segments, which are all in around 60–70 billion size. So that is where a lot of further development will also happen. So overall, this 2021 market size was $590 billion. And as previous foil was saying, this will almost double to $1 trillion now. And we see a very clear linkage between the semiconductor revenues and the GDP. So this is where that is a proof point where you see the kind of linkage. And if you look into the value, and I think Josh has presented that yesterday already, there is from each semiconductor dollar a major impact to the GDP. So one semiconductor dollar creates a $13 on the GDP level. And that is where the major opportunities are coming in also for the semiconductor to further grow into the GDP and create more GDP overall. So this is for sure a very high attention to each country, to each economy, and semiconductors are getting more and more strategic in a lot of products. So now going into the leading technology topics. I picked a picture from a long time ago. So in 1954, a newspaper published the vision about how a home computer could look like in 2004. So people at that time could not imagine what's happening over time. And I think we are all aware how a home computer looks today, quite different. It also looked 2004 quite different. So all that due to the innovations driven by the semiconductors, and Moore's law was really kind of guiding us in how this should develop. And I looked into the material and I was very astonished myself as I saw from what kind of data level Moore took the conclusion that every second year the transistor number will double. So he just, on the left side, you see this chart, has a few points where he saw some historical transistor number data over time, and he saw that big innovation which may come in semiconductors and predicted it. So what does it mean, Moore's law? We are hitting into the direction of 1 trillion transistors in a semiconductor product in 2030. Today, we are at 100 billion. So we have a product at Intel Ponte Vecchio, I come to that later, which has 100 billion transistors already. So we are on a good track to follow this innovation guidance from Moore's law. But we also have to say we need to combine now the silicon and the packaging innovations together. So in the past years, we lived from the silicon innovations alone. Since a few years, we see that we're combining advanced packaging solutions with advanced silicon solutions into one product. And this will continue, and this will even get stronger. So semiconductors are the new oil. So what we see is with the superpowers, which I just mentioned, we will drive for more and more compute needs. So we have seen the simulation of full immersions. We will look into the simulation of intelligent avatars and bots. We will see also this little dot, the empowerment of everyone. So everyone will have a chance to get as much compute power as he needs to create, to innovate, to do whatever. So there's a lot of further movements and needs to increase the compute capabilities in semiconductors. And we even will go into the simulation of a full virtual economy. So this will drive the need for more compute over time. So this chart shows now the Foundrie market feature dimensions, meaning the technology features. So the light blue one is the more mature nodes. The middle blue tone is from 16 to 5 nanometer, and the dark blue is smaller than 4 nanometer. And what you can see is that we are moving very strongly into a very advanced node market here for the foundries. So we are getting almost to a 50% share in 2030 with the advanced nodes. And all this is driven, again, by those typical topics like the cloud, AI, the connectivity, and the intelligent, the edge topic here. So on the technology side, and I don't want to go into the details of each innovation, but Intel always was a driving force in the semiconductor innovations on the CMOS technologies. Over the years, we introduced a lot of new features. So today we are in the 3 nanometer high volume production. So we are getting ready to enter the angstrom era. So we are talking now about a 20 angstrom, 18 angstrom technology and bringing in new innovations there. And please don't take the angstrom naming as a physical dimension. This is more kind of drawing further what we have started long back with the planar transistors and kind of predicting the performance it would require kind of such kind of dimensions on the planar transistors. So we left that road already with the FinFET technologies, and we going into the gate all around. So this is more the naming convention which is worldwide getting established. So as I mentioned, we are on the way to combine silicon innovation and package innovation. And again, Moore was already predicting that there is a time to come where we will do so. And he predicted that it is more economical to build large systems out of a smaller function, which are separately packaged, and interconnected. So that means we are combining now really the packaging innovations into the silicon innovations. And we are coming from the more traditional packaging technologies from wire bond and flip chip into technologies where you combine the chiplets of different technologies or same technologies by a silicon bridge or by a silicon interposer substrate and building complex systems out of it. So here, this is a kind of approach which you see in the market already since a few years. And this is starting off with IDMs or fabless companies who have ownership in each of those chiplets and combining those. But we will see that also in combining different chiplets from different sources in building new solutions. So a few examples here would be from Intel side on that page. So we are in this transition from a system on one chip going into system of chips. And a chiplet you can see as it will have a certain IP block in the chiplet, and you need to combine different IP blocks of those chiplets together in one kind of product by standardized connectivity between those chiplets. So what you have seen in the products, for example, on Sapphire Rapids, which is a data center product, is that you have 4 compute dies combined directly with a memory interface, with the memories in the same package to build a most high performance and power optimized system. Lunar Lake, a client product for laptops, also getting introduced, is combining here a compute chiplet with an I/O hub being in a technology which is not the leading technology but before. So I/O hub chiplets you can kind of reuse through different generations. You are not forced anymore to migrate all the IP always to the latest nodes, but you can keep some standards in the node where they best fit and concentrate your design work in the next node on really those compute chiplets, for example, which bring the most value out of it. And also here you combine the memories directly into the package. Then you have Ponte Vecchio, which is this 100 billion transistor product. It is built out of 47 different chiplets out of 5 different technologies. So it's very complex, but it's a highest performance, highest density supercompute application here, and this is where you see what is possible on those new technologies. Silicon foundries. Now coming to the general part of silicon foundries, manufacturing. So in the early days, the integrated device manufacturer have done everything. They have designed, they have developed the technology, they manufactured, they packaged, they sold the product. So this is a typical IDM. In 1987, Morris Chang came back to Taiwan and founded TSMC. And the vision was to create a company who is specializing on the manufacturing services only. So in the early days, he worked together with IDMs, and the IDMs said, I have some products I don't like to manufacture anymore. This is old stuff. I bring it over to TSMC. They manufacture it for me. I don't need to take care for it. But this developed further and further, this business model, and it created also companies, the so-called fabless companies, who are today designing into directly TSMC. They never had any capabilities to manufacture their own devices. So the new business model now establishing besides the IDM concept is to have really manufacturing services as companies and fabless companies who are making the design and which are selling the final product. So this is very important, and you see the big names here, and this is where a lot of the worldwide major products get generated meanwhile in this fabless in combination with silicon foundry business. What you also need to understand is that over time a lot of changes happened, and due to the high cost of the manufacturing, the industry consolidated. So on the left side, you see in the 90 nanometer, which is around the year 2005, there have been still plenty of companies being able to develop this technology, to design, to manufacture products in that technology. Only a few years later, you see this is already reducing because a lot of companies could not afford anymore to invest into the technology development plus the manufacturing capacities. So means nowadays, since about 10 nanometer, 7 nanometer technology, there's only 3 left. So there's Intel, there's TSMC, there's Samsung. That is the 3 companies who keep racing on the technology development and building the global capacities. So this is where things getting consolidated, and referring back to the message of, hey, but 4 nanometer and lower nodes are so important globally. We're putting all to 3 companies. And that is where a lot of the concerns also on the geopolitical topics rising, because the dependencies on those 3 companies are now very visible. How do I do the turn? So I'd like to talk a bit on the semiconductor value chain, because it's important to understand that the Foundry has established a very strong collaboration through the ecosystem. That is a major difference to an IDM who needs to do everything on their own. So the Silicon Foundry is concentrating their business around wafer manufacturing, but also on the silicon technology development. And they are partnering up with the ecosystem partners, with the EDA companies, with the IP companies, with design service companies, to provide the capabilities to make a design into their technology. And this is the kind of way for fabless companies to leverage the technologies and manufacturing services of foundries. So this portion here on ADA, IP, and design service is super important to make this business model work. The other side, the assembly and test, in the early days of silicon foundries, this was not owned by the foundries themselves, but there was a second kind of business model establishing, which was concentrating on manufacturing services around assembly and test. So typical members of that category is ASE, Amcor, and those guys. What we see over the last years is that the silicon foundry is also starting to invest into advanced packaging, because a lot of the technology on the silicon side is very much linked into the capabilities of the packaging. And as I explained, the new product, the new trend of chiplets and advanced packaging even is pushing that forward, so that you see meanwhile that the silicon foundries are also providing the packaging solution for those complex systems. So, and as some of you may be aware, this is also one of the capacity bottlenecks currently existing, where, for example, NVIDIA's artificial intelligence solutions are driving such high demand in the packaging that the capacity is short, and TSMC is currently doubling their capacities every year on the packaging side. So around all this ecosystem, there have been established other services like shuttle prototyping services. Famous example here is the Euro practice, which is very established, and also ASIC turnkey services where companies help other companies to really make silicon products happening, which those companies would not have the capabilities to do so. So now looking into the foundry market of today, last year, 2023, this market size was 120 billion. So it's really big, and it grows roughly with some 8, 9, 10% per year. And what you can see is that TSMC is leading the pack here by far. So they have a 58% market share. And this is where they are kind of dominating a lot of those market dynamics. The second one, Samsung Foundry, having a market share of 11%, and then UMC Global Foundry and SMIC are following with some 5-6% only. So what we also can see is that 87% of the foundry wafer manufacturing is in Asia, which is perceived by many people to be not balanced, because a lot of the consume of semiconductors is happening on the Western world, but the manufacturing of semiconductors is very much concentrated in the Asian side. And there's some geopolitical issues which could happen, which could be a major disruption to the semiconductor supply chain. So that is a general concern. Now coming to Intel System Foundry. I started already with this page in the beginning. So we are the world's first system foundry. So we are more than just the silicon foundry. We go on the latest trend to really say, hey, there's more than just the silicon. There's silicon packaging. There's even chiplets. There's system integration happening. So this is topics which not every customer can do themselves. They need services around those things. And that is where we are building up our business model. So as you see, we are providing the world-class foundry offering. We are also focusing on resilient and sustainable supply, and providing the system of chips capabilities and services. So putting that picture into a little more details, you see on the bottom side the typical Silicon Foundry offering profile with technologies plus the ecosystem providing design flows, IPs, and those things. We put on top of that a strong focus on the supply topics, so being secure, sustainable, and resilient. Then we are putting a lot of innovation also into the packaging side, because we are a strong believer that this combination between silicon and packaging will make the difference. And driving kind of industry standards like the UCIe to make sure that even from different sources, manufacturers or designers, different chiplets can work together by standardized interfaces. So we are definitely like to have a kind of an open standard to make sure that different chiplets can be combined. And not to underestimate the software piece going to those systems is very important. So, talking about our technology offering, so we are pushing forward and we are extending our roadmap, coming up every second year with a new major node. So our portfolio starts from Intel 16. We have established a joint development together with UMC on 12. Then our major technology base is Intel 3 and Intel 18A today, and we are looking forward to introduce the 14A and the 10A. So this is where we are differentiated to other foundries, where we are focusing very much on the advanced leading nodes, and in our portfolio you will not see yet the mature nodes. Talking about new innovations, especially coming into the Intel 18A, so the Angstrom era, I wanted to not miss out to give you a little insight of two major innovations which are coming in here. So I hope most of you are aware on the FinFET, which was the first way going beyond planar devices, really going into three-dimensional devices by FinFETs. So with 18A, we will go in full 3D and we'll go into a gate-all-around device structure for the transistors. So this is called RibbonFET, and this will lead to even better performance per watt and Vmin. So this is a big innovation on the transistor side. The other big innovation is on the metal stack. On the left side, you see here the typical metal stack of a technology. So you have in the gray area, on top you have the devices, and then you have all the metal wiring in the different layers above it. So this is a classical way to make a technology. With 18A, we introduce first time to have the transistors in the middle. So you have the devices in the middle. You start processing the standard functional wiring to the top, but then you turn over your wafer, you thin it down to a very thin layer. And then you go down from the backside and put the power metal on the devices from the backside. So you bring the powering of devices much closer to the transistors. So this is majorly improving your power efficiency. So your loss bringing a power from the top to the transistor can be massively reduced if you go directly with fat wiring from the backside to the transistor. So, talking about silicon technologies and now also on the packaging technologies. So as said, there is the more conventional packages which we are not so much focusing on. So flip chip for large chips is definitely a focus topic, but then our major focus goes into the advanced packaging. So the EMIB technology is a packaging where you use standard substrate, but you embed into the substrate a silicon bridge. And this silicon bridge makes a connection from the two chiplets through the silicon bridge directly, and it is very efficient and high performance connections. This is a one way, this is a cost effective way for such a package. The other traditional advanced packaging way to do it is to really put under the chiplets a full silicon substrate and to connect through that silicon substrate the different chiplets. Or you can combine both technologies, or you even can go in more micro bumps for those connectivities. So this will be further developed over time to get more high performance connectivity, more dense solutions. So besides our technology offering in silicon, in packaging, we for sure also working very closely with our ecosystem alliance partners. So you see here our partners from the EDA side, from IP side, design services. Meanwhile, a lot of design work happens in the cloud, so the cloud enablement, as well as in the US MEC, that is the US government programs where there is a special setup of partners. So now going into the supply chain topic, the resilient supply chain for advanced technologies. So you see in this map, our manufacturing sites are mainly focused in the US and in Europe. So in Europe, we have a very high volume manufacturing site in Ireland running already, a second one in Israel, and the third one is in the planning stage for Magdeburg in Germany. So this will come up in 27, 28. On the package side, we are also planning in Poland to have a site. So overall, we also have in the US a lot of more investments. You see, Intel really takes huge investments now over the next years to build this capacity in the Western world and to enable the US and the EU to be more sovereign in the semiconductor products. So talking about Magdeburg, you probably know from the newspaper, we are talking here about a 30 billion euro investment. So we are planning to have 2 fab modules there in the beginning, and we have not finalized the technology node, but likely it is 18A and beyond, probably beyond, depending on the demand situation as we invest. On the Poland assembly and test location, that is where we also heavily invest with 4.5 billion euro. So this is enabling a supply chain within Europe for semiconductor products. Why is it important? If you look into how the advanced node capacities will look like in 2027, you see in the inner circle would be the scenario if there is no Intel. So you see rest of world, the dark blue one is very small. So mainly everything is Asia. With Intel, we make a difference. We target to have a 29% of capacity being in the US and Europe. And if you look into capacity specifically not in Asia but in US and Europe, you see that Intel is by far the biggest one really investing and driving these capabilities in the Western side. But not only that, we are also recognized in leadership for sustainable manufacturing. So we are putting a lot of effort also into our green activities on the water, on the waste, on electricity and others. So this is where we have another strong focus to make a change happening. So now let's talk about semiconductor attractiveness. So we currently have a perfect storm reshaping the semiconductor industry, I would say. We have a supply chain which is re-architecting. A lot of changes happening around the supply chain. The other one, with the AI, there's a lot of structural shifts in the customer needs. So a lot of end products of different segments asking for compute, for AI. So this is where a lot of new innovations, new opportunities coming up, which makes our industry so attractive. So either if you are more interested in technology, manufacturing aspects, there's plenty of opportunities. We have rising costs, so a lot of investments going into it. Where the money is also great talents needed to manage all those things. There is an over-concentration in Asia, which a lot of companies, not only Intel, trying to make a better balance through the world, which opens up opportunities, and the climate change is another great activity, attractive for the talents. On the structural shifts, on the customer needs, what we see is that AI, HPC, has surpassed the mobile revenue, so was not foreseen in 3 years ago. So this was always believed, oh, smartphone is the biggest market, there's nothing else. Now we see that AI gives an addition to the HPC business, and this will really grow further and will be the largest business opportunity. Then you have this big trend with the systems of chips, which are opening new opportunities, new architectures. So this is where in 2028 we expect that those chiplet solutions surpass the monolithic solutions. And then you have the vertical integration. So a lot of OEMs are aware that they are very much dependent on silicon products. They see silicon products as their strategic need and investment to get a better control and innovation into their own products by semiconductor products. And one example I like to raise is automotive, where there happened already a lot over the last decade. So the left picture is showing already that the semiconductors has gone into the car everywhere. It is today already with, I don't know, 100, 150 compute solutions within the car, a massive dependency of the automotive industry to the semiconductors. But what we see in the future, there's two big things happening. There is the electrification of the cars, which you see in the lower part of that picture, so the battery, the power management of battery. This is a big thing where a lot of semiconductors going into it. But there's another big thing happening, the digitalization. The autonomous driving or the driver assistant systems, which require that you get a central compute into the car and that you connect the central compute with some zonal compute functions where you have a lot of the sensors connected. And this will totally re-architect how the car electronics is done. And this opens up another big opportunity here for advanced nodes in this central compute part. So this is highly attractive, and for automotive we have a very strong hold here in Europe, and we need to really keep that and go forward. But even if your interest is not so much in automotive, there's plenty of other segments. So semiconductors are everywhere. So that is where it's great to work in this environment. It's a growing environment. And from the EU side, you have a situation which is great because now the politicians are really pushing into it, putting a lot of money into it, and putting up targets of a 20% semi-manufacturing share in 2030, but not only the manufacturing, they are also investing into accelerating this leading-edge chip design capabilities, making the materials and equipment suppliers stronger, making everything green, and also putting a lot of efforts into developing the talents. So this, we can benefit all from that, and we are closely working with the EU in a lot of those initiatives to make these things happen. So going more into the details, I talked about all the big investments we are doing here in Europe on the manufacturing side, in Germany, in Ireland, in Poland. We are putting up silicon foundry services, system services being available here in Europe, so please contact me if you have needs. And we are also having established a lot of research and development partnerships here between Intel and a lot of the organizations. So we are working with universities in a special university program. We are supporting startups to guide them, to help them. We are working with a lot of the research institutes through Europe. So we are very active in the overall setting, and that is great. And we are truly building history together, and let's make it. Thank you.
Tenemos 5 minutos para unas pocas preguntas, several questions before you leave.
Thank you very much for the presentation. Okay. I'm Rubén Pérez Aranda, CEO of KD. It's a fabulous company here in Spain. We are focused in automotive industry, providing to the automotive industry optical transceivers, multi-gigabit optical transceivers. So I would like to know what the reasons why Intel Foundry focus on nodes of 16 nanometers and below, and is not focused 22, 28 nanometers that where the automotive industry have most of the manufacturing. And I would like to know also if you are going to provide to the fabless companies automotive quality service like TSMC provides for similar nodes 0.5 automotive.
So, coming from Intel, you have to understand we do not have technologies in higher than 16 nanometer. So for us it would be a totally new investment again. And this investment needs to be really thought through because there is a very highly competitive environment for those nodes. And those nodes in our competitors are depreciated. So if you come in with a new investment, you need to kind of earn back all your equipment investments before you earn the money. And the other competitors, they have earned the money for the equipment already. So this is a very highly competitive environment. And we choose to not be in there, but to focus on those things where we have most company focus anyway on it, and where we also see a very high growth coming, meaning advanced nodes, leading nodes. Second question on automotive. Yes, we are planning to have also some automotive technologies in our portfolio. We are currently working with some customers to evaluate what we want to do. So we can have a talk later.
Yeah. Well, what's the main reason that made you consider packaging at the design level? There has to be a reason as to why. You said in the advanced packaging, you say the packaging comes even at the design level where packaging has been traditionally separated from the design of the chip itself. What is the main reason that made you do that?
So up to now you have seen the design technology co-optimization happening. What happens in those more complex systems in advanced packages, you need to really do a system technology design co-optimization. So you need to really think it through how your architecture, how your data flow, how your bandwidth between the chiplets need to be. And therefore the kind of packaging technology is an essential part of making the design. Is that answering the question, or?
Well, yeah, I guess you're talking about these changes from the von Neumann architecture and a very complex architecture, and I was more into one detail. What are those details that make you do that? I mean, what are the chiplets demands that make you agree?
It is definitely compute-based, so high bandwidth exchange, combining chiplets with the interfaces to the outside, but also meanwhile it is more economically to build smaller chips due to yield issue, or no, due to the yield which you can achieve with the area of the chip, and you build two compute chiplets and combine those instead of doing one bigger one. So it's economically driven, but definitely those advanced packages are more on the purpose for compute application, not so much on, hey, let me combine an MCU with a sensor or whatever. This is a totally different package.
Okay, one quick question. Now that you mentioned about the connections and the speed of connections for computing, where do you see photonics in this? Because you mentioned a lot the silicon, and the question is, where does photonics come in? Do they come in as chiplets that add more pressure on the standardization of interconnects?
So we are also providing services around photonics. So we are working with our kind of internal photonics BU, and we can connect through the package photonics into those systems.
So it's not wafer level, it's through the package?
It's in the package.
In the package. So it's a wafer level packaging?
It's chiplet-based package. So it depends how, I'm not an expert in this.
Okay.
So need to connect you if you are interested.
Okay.